Let me just show the presentation slide. Sorry, I don't do the live coding because I'm not good at it. And okay, here's my slide. And today I want to talk about this. And so, hey everyone, my name is Yasuhiro Inami, and I come from Japan. And this is my first time to visit Budapest, and it's a wonderful city so far. And I'm very happy to speak in this Functional Swift conference. And I'd like to thank Agnes, Chris, Brandon for organizing this and inviting me here. Today, I would like to talk about type-safe URL routing in Swift, and I hope everyone will enjoy it. By the way, I'm working at a company called Line Corporation. And this is a messenger app platform, and it's based in Tokyo. And we develop many kinds of other apps like camera, music, news, games, and so on. So if you're interested, you can talk to me tomorrow. Okay. Anyway, let's get started. So what is URL routing? We can think of it as a mapping function from URL request to response. In practice, we often handle the side effects too, such as read and write from disks and sending the data to the socket or showing up the UIs. But today, I will only focus on the simple stateless model, just parsing the URL string. Suppose we have a URL like this one, say funswiftconf.com and the hello Budapest 2016. So the host part is funswiftconf.com, and the path is hello Budapest 2016, and this looks like an awesome page, and we want to handle this one. So since the host name is just an entry point, we don't have to check it and just concentrate on the path part. And with URL routing, we can use pattern matching to extract the city and year, for example, in this URL example. And by doing this one, we can also extract other URL example, such as hello Tokyo 2020 or something like that. And this kind of URL routing can be found in everywhere. For example, in iOS app, we have a universal link since iOS 9. And we also had, or maybe we're still using it, iOS 8's custom URL schemes. And this is the client's app side, and URL routing is more common in server side, such as Perfect, Kitsura, Zero, Vapor, and etc. These are all famous Swift 3 server-side frameworks. And most of them are inspired by modern web application frameworks, such as Node.js's Express. Now let's make a bit of simple, but a bit naive in this case, but URL router from scratch. Let's say we first prepare the enum sitemap that declares only two URL patterns. One is the case hello, which has two associated values. One is city as a string, and one is the year as an integer. And the other is case not found. For the first case, sorry, I just said that. Then we create struct router, and with the function match. And then maybe we can implement something like this. Say, I use the function helper, myregex, that basically extracts the path components using regular expression. But please notice that this function returns the array of string, but we rather want to have a string and integer. So actually, this is not type safe. And because of that, we have to assure that this captures exactly has a count of 2. And also, we can convert to integer. And once everything, the parsing succeeds, we can return the sitemap.hello like this. And if the parsing, the capture failed, we can just return .not found. And to use that, this router is easy. This is an example of iOS's universal link. And we first check the activity type to make sure that it's from universal link, because this method, this is the delegate method in app delegate. You also have handoff and like spotlight search APIs, so you have to check that first. And after that, you use the router and with the function match and use your pass in and get the sitemap and do some kind of side effects. So let's say if you get the hello, and then you can maybe present some awesome movie view controller using it, using the associated values. And if you didn't, if you get not found, just like print error log and do nothing. And here's a naive client example. And how about let's take a look at server side. In server side, we already have a built-in URL routers available. Unlike my previous regular expression example, many of them uses the data structure called tries or prefix trees, and that improves the performance. As you can see, the syntax is very easy to read and has a very similar syntax as Node.js Express. For example, in 0, we write something like this one, and we call function get with the passing the pass pattern and the request handler. And the pass contains a colon. It indicates that we are going to extract this other parameter. And inside the request handler, we call request.pathParameters and pass the string key. And this will, you can extract the captured value. But wait a minute. We still find the same problem here, and that is we still extract the parameter as a string. And this is obviously not type safe. And even worse, we want to extract the year as a number string, right? But this doesn't really indicate it's a number or not. So we have to double check it and in order to safely convert to integer. And that's quite cumbersome. So how can we improve this situation? If you take a look at the Vapor code example in the last line, in Vapor you will write like something like this. Instead of passing the single pass pattern, you pass multiple values. And some of them as type variable. In here it's hello and then comma and string self, this is a type variable, and then comma and int self, another type variable. And by doing so, believe it or not, in Vapor you can immediately get the type safe request parameters, as you can see this code. So it's like, wow, type safe. So yeah, it's happening, you know. Have you tried Vapor? It's really happening. But we wonder, how is it possible? So let's take a look at its internal code. And here's actually the internal code. I took the code from the file name called generated.swift. And as the name says, actually, as you can see, there are tons of function get. These all generated from other script file. And each describes the particular path pattern, such as the top one is get with a path component, single path component only. The second one is single wildcard only. And then the third one, path component, then wildcard, and like path and then path, and the wildcard, then path, then wildcard, and so on. So, and obviously, there are lots of other patterns as well, right? So you have to list all of them. And that looks like a hard work. We can say this is a part of meta programming. I don't say this is bad, but this is something we should at least try to avoid. So please imagine if you want to handle this kind of path pattern. Unfortunately, Vapor only supports up to 3 path components. So what happens? We just have to give up. So we can't use the same technique for a very long URL pattern, and that's a sad thing. But that doesn't mean we have no other way of guaranteeing the type safety of URL routing. Fortunately, we have a great tool called functional programming. And right, that's why we are here, right? So, and to think about type safety, functional programming is always our friend. So let's take a look at one of the most beautiful functional programming technique here. And actually, that's me. No, I mean the parser combinator. This is a talk I gave on March in TriSwift conference held in Tokyo, as Chris just mentioned. If you missed it, the video is available at the Realm's website, so please check it out. And also, Chris, right there, he also talks about it in Swift Talk in Objective-C.io. So I definitely recommend to watch it as well. So what is parser combinator? In a nutshell, you can think of it just as a functional way of parsing text, character by character. It is useful for any size of parsing, so such as even making a compiler, for example. But in our case, that's a bit too much. We don't need such powerful parser for now. So, but still, we can use the same idea here. And that is, instead of parsing each character, we just treat a path component as a single unit and parse string by string instead. And this will make a URL parsing a lot easier. And now let's implement the URL routing parser using the ideal parser combinator. First, we create a simple struct root here, and it has an internal parse function, and which basically takes path components as argument, and it returns the tuple of remaining path components and the output generic value. And because the parsing may sometimes fail, we use the optional in here. And this kind of structure is called state monad, and with the optional monad inside. And if you have watched my previous Realms talk, I mean the TriSwift talk, the structure is almost identical to struct parser. So please check my video for more detail, actually. And the difference is that this takes an array of string as an input. But in parser combinator, it's basically just a plain string. Next, let's add a functor, map function. In Swift, we often use the caret symbol with the angle bracket, like this. And we implement something like this code. The function f is given on the left-hand side and the root on the right-hand side. And what it does is, first this one here, root parses the path components and gets the reply. This is the actually optional tuple. And we check that. And if the parsing succeeds, there has to be some values. And the path component 2 is the remaining path component, and the value is the output. And if the parsing succeeds, you apply the f to the value, and you return that as a result. And if the parsing fails, you just return nil. And actually, this is totally the same as parser combinator talk I gave. And this is the next one is applicative style, or applicative functions. And I won't actually repeat because I think I don't have much time to talk. There's a lot of other things to talk, so I will just skip explanation for a while. You can just implement a function like this. And so here's the function pure, and here's the function apply. And can you see here it's a double star, and it's a flipped apply, and the next two are the discardable sequential applications. And we can also add alternative functions too. It has basically function empty and alternation functions. So far we have talked about functor, applicative, and alternative. And we might think next, we can also implement monad as well. We are all functional programmers, so we all know about these, right? And actually, we don't have to implement monad. And why? Here's the reason. We don't need monad because when we make URL routing chaining, the previous route doesn't really affect the next route. And this, in formal language, we call this context-free grammar. So that means there's no need to create a new route at every runtime. And yeah. And if you can implement flat map if you want the monad, but if you keep using it, it will actually degrade the efficiency, and you can't even optimize things. So in my talk, we will avoid implementation. So instead of implementing monadic parser, we implement affiliative parser instead. And here are some important functions to discuss too. The first one is the func capture, and this basically takes the parsing function that's from converting from string to some optional value. Let's say integers initializer. That is like a favorable initializer, for example. And inside the implementation, you first decompose the path components using the function called uncons. And you get the first and the last of the path components. And you apply the parsing function to the first path component, and you get the parsed value. And everything succeeds, you return the rest of the path components and the parsed value. And if this process failed, you just return nil. That means parsing failed. And by using this function, we can implement many more other routes that are type safe. For example, the second one, funcInt, that basically captures integer, that converts string and it makes it integer. And like you can also implement funcstring, for example, that just convert and doesn't convert maybe outputs the string. And if you're not interested in capturing things, you can like declare the function match. I use the capture here, but actually capture and matching is mostly the same, except it does output or not. So just I use the capture here, but I'm not interested in the output value, so I just return the void here. And the last one, the function choice, is you receive the multiple routes and choose which one is the most favorite one. And you can write something like this, the folding, reduce using reduce, and like that. And now we are all set, so let's try parsing. The upper part is an example of parsing URL pattern, hello city year. And as you can see, this code is using applicative style writing with the curried function on the top. And then map comes next, and the matching route with the hello comes next, and followed by applying and consecutive routes. And inside the curried function, the $1 represents a string, and which is captured by this string route. And the $2 is actually integer that is captured by integer int route. And please notice that the whole this process is now a type-safe output. And if we run this route like this one, hello Budapest 2016, maybe you can use like just URL with the path components. You can just split into the path components, right? And you just run it, and you get the Budapest and 2016 with a type safety. Yeah. And on the other hand, if you return some kind of wrong URL, like Yasuhiro, and yeah, you get nil because the parsing failed. And here's more complex example. And let's say we want to parse character R first, and then we want to parse one of the following paths. First, we checked foo string and try capturing integer. And if everything succeeds, we return sitemap.foo. The second one is we checked bar and then try capturing double. And if that succeeds, we return bar. And third one, we check bars, buzz, and capture string and return buzz. The last one is we don't capture anything. We just check foo, then bar, and we return foo bar. And if the URL doesn't match to any of these routes, we can just simply return not found. And let's test this. The above code is just the previous one. and the test code is the bottom. As you can see, all works like a charm with type safety. So it looks good to me, a happy ending. But wait a minute. Is this really the best way? We should take more closer look at the code once again. This is the choice function I extracted from previous code. And if you take a closer look, you can see that we are checking match foo on the first one and the fourth one. We are checking the foo string twice. And actually, this is not an efficient way of implementing things, because we check foo, then integer, and that fails. Like you check foo again and check bar, things like that. So you don't want to repeat the same thing, right? And actually, we call this backtracking, and that's an unintentional backtracking. We rather want to implement the routing like this one. So we want to group the match foo and then like add one nest deeper choice, and you write like something like this. So that once the foo matches, then we only check the choice, and if that fails, we don't have to do things again. I mean, again. But rewriting the code into this one is maybe easy, writing by hand, but sometimes we make mistakes, right? So it will be great if we can just press one button and convert to this one, right? So we want to make optimization easy, and to do so, we will dive into the enum-based routing instead of the function-based one. Let's take a look. Here's a new route type using enum instead. And in here, I used indirect enum because this is actually going to construct the recursive enums. And let's take a look at each case. The first one is case match, and it takes two associated values. One is the matching string, and the root is, second one is the next root. And the second case, capture, it takes two functions as associated values. One is converting from string to some value like integer, optional integer as I just mentioned. And then second one is the conversion from integer to the next root. Actually, these two functions can be merged together into a single function. But I intentionally separated these two because it makes first function as keeps the identity of its function. So it's good to separate these two. And I used any here twice, but actually these types should be the same. But in Swift, we cannot use the generics for the case. So, and this is actually called existentially quantified type. Actually, yeah, I'm not quite sure how to pronounce it, but yeah, you can't use generics. So, and in Haskell, like it's for all. And for Swift 3, for now, I will just work around using any here. And the third one, let's talk about third one, the case choice. We just received the multiple roots. And this is just works same as the function choice I just previously mentioned. The fourth one is case term. This is actually a terminal root that only outputs the value and doesn't consume anything. The last one, case 0, we don't output anything. This means just the post is failing. And what's good about making these enum-based UR root is that we can now see the structure of the tree, and we can make an easy optimization. But before doing that, we have to implement this func lang, because we moved to the enum-based. That means we lost the functions. And we have to re-implement this one with using switch self. And I just omitted the code here, but you just declare like this. And also, don't forget to implement functor, applicative, and alternatives too. And eventually, this works just same as before. And here's the fun part, optimization. To optimize a root, you implement the code something like this. For match and capture, we optimize to the next root. like this. So it will optimize recursively. And for the choice, we will call optimize choice function. And the code, the implementation of optimized choice will be like something like this. We first sort the roots in ascending order, for example, and then we arrange it by using the function helper function called group by. Actually, this is the method I just implemented, and it's also in Haskell actually. And you group it by the same root head, and yeah, it will make an array of roots. And you have to flatten it, so you call it map flatten here. And this will make an array of roots. And you return with a choice here. And we are all set here, and let's optimize this one. Here's an code before optimization and after optimization. And all the implementation, this naive root is actually the same as before. We have two duplicated match foo here. And you just optimize, you just call optimize function to make an optimized root. And what happens is the top one is the naive root and the bottom one is an optimized root. You can see that the match foo is now merged into a single node, and we have a subtree like this. So yes, we could make an optimized URL root in a very functional way. And actually, just 1 hour ago, I just open sourced this fun router. So please check it out. So you can just see how the code works. And I also added a playground for it. So maybe you can enjoy, and maybe you can, if you have a question, you can like ask in tomorrow time. And let me just talk about summary. And we just talked about many URL routing examples, but most of them are basically a string-based capturing, and that is type unsafe. And it's not easy. It's easy to write, though. And to make a type-safe URL routing, we will dive into applicative parser instead of monadic parser. And by changing the root type from function-based struct to the enum-based one, we can now do the optimization. And lastly, here's one big caveat, unfortunately. But current Swift 3, if you write too much functional code, you get too easy to get error. Expression was too complex, blah, blah, blah. So yeah, that's not what we want. I mean, we can make a code subdivided into pieces, but that's not what we want, right? So I hope Swift 4 will surely improve this one. Swift team to improve this situation. So this is it for my talk. Thank you very much for listening. And I will hear any questions. Yeah, I can take. Sorry if I couldn't hear the English. I'm not very good yet also. Okay. Anyone? Okay.
Do you think we can use this parser combinations of other things than strings and app components? And do you have any other ideas?
Other than string? You mean the string as not the string as an input? Yeah, in one different. Actually, I cannot think about that. I think there are many ways of situation that the parser combinator idea can be applied to other field or yeah. But currently I cannot think very much. Okay.
So first of all, thanks for showing what you showed, because this has restored the confidence that in our code base we're saying we're not the only ones doing these crazy things. And on top of that, I wanted to ask you, do you use any functional library that gives you these operators? Because, for example, we do you use any of this, or do you have to find your own?
Actually, in Swift 3, it's quite hard to use the operators, and because we are now having a precedence group, right? And actually, if you have like multiple flat map symbol, like I had a situation where the result framework and the runes framework. Actually, that's released by Saltbot, I think. And these are having both flat map operators. And if we import both libraries and try to use the flat map, actually we get the error. And what we have to do is to like overwrite it and to overcome. And so I think I'm actually trying to use the runes as an unified operator library. And I'm not sure if that's the best answer or not, but I think we have to like put, how to say, unite together and make, yeah.
So do you think that operator should be namespace?
Yeah, I think so.
That's just something that's lacking.
Yeah, true. I also want like, we can do partial import, but actually I don't know good way of doing for operators. I think we can do it, right? Okay. Can? Can't? Okay. Yeah. Okay.
So, in the context of the optimization thing that you showed, I was wondering if that was something that you did just for fun, or you actually had some performance issues, because it seems like micro optimization in most cases, in most use cases.
Okay. Yeah, I just made it for fun because I actually in a previous talk I made a parser combinator called try-parsec. And actually, it didn't have much good performance. And I'm kind of just not expecting the performance too much and just play for fun. Yeah. Actually, if you write too much routing, yeah, you just get the expression was too complex error. So I think that's something Swift should evolve even more so that we can hold this kind of conference next year. Yes. Correct. Actually, no, in this example, I didn't do it, but you can use like permutation parsing. And actually, I implemented recently in a try-parsec, parser combinator. Yeah, I think we can use that idea. Yeah. Okay.
You have mentioned that the compiler is having a hard time opening those complex expressions. My question is whether these expressions or this code in runtime does it have a performance penalty compared to like gets?
Yeah.
Benchmarks perhaps?
Yeah, I tried benchmarks in parser combinator, but there are many penalties actually now. Yeah. So.
Does it mean that these expressions are not just complex to compile, but they are also slower than?
Yeah, slower. Actually, because I think some kind of inlining may be necessary for generic function call. I'm not sure if that's the right answer, but yeah, I had it in a previous talk, and in Swift 3 still there are problems too. So yeah. Any other questions? Okay. Thank you very much.